Okay, maybe we'll start. We're very happy to have Dr. Rodriguez from Princeton to give the first seminar of the semester. He'll tell us about Virasoro minimal string and Liouville string cosmological.
Thank you so much for the invitation, and hope everyone had a good break. So today I'll be talking about this paper that came out last September, but I'll also mention at the end a couple of other papers I wrote earlier last year about a different interpretation about the same model. Although today we'll mostly focus on the Virasoro minimal string. Okay. So before that, let me just flash through my collaborators: Scott Collier, Lawrence Everhart, and Beatrice Bowman. So this is working in collaboration with them. And here's a brief outline of today's talk. We'll first start with a short introduction, just to put things into context. What are the sort of main ideas that have been floating around that we're trying to make progress on, and which is low-dimensional string theory, broadly speaking, but also low-dimensional models of quantum gravity. Okay. So part one, which will be most of the talk, would be about the Virasoro minimal string and how we think about this from a 2D quantum gravity perspective. Part two, which will be rather short, we'll talk about what's perhaps more the usual way we think about string theory in target spacetime. What is the interpretation of this model? And then we'll end up with a summary discussion. Okay, so let's get started with the introduction. So just a few words about low-dimensional string theory. So they provide very rich laboratories just to understand more fundamental aspects of string theory in a very simple context. So much simpler than higher dimensional superstrings, for example, in 10 dimensions. But still, they still exhibit rich and interesting phenomena that we would like to study in the simple context. For example, here's 3 examples. They still exhibit holographic duality. So and also the stringy ones. So these low-dimensional models gives you, for example, an opportunity to try to derive them or try to understand what the underlying physics under holographic duality. Another rich phenomena that is also present in these low-dimensional models are non-perturbative effects. For example, the instantons is a particular class of non-perturbative effects in string theory. And these are much simpler to analyze in this low-dimensional models. So one, for example, that I work with a member here of NYU, with Bruno here. And last, another thing that has been notoriously difficult in string theory, it's time-dependent phenomena. A famous example of a time-dependent phenomena is rolling tachyons. This is a review by Asho Sen, and some other fairly recent work for also people here in the audience, Bruno, and as well as Dote and Hurbet here. And so again, the philosophy is that in this low-dimensional models of string theory, this rich phenomenon might be simpler to study in detail. Nevertheless, Worldsheet string theory is still it's a difficult thing to study in the direct Polygon formalism of integrated correlation functions of CFT over moduli space is still difficult, but in these models are perhaps a little simpler. So here's just 2 examples, just to put more context. So a couple of examples you might have heard of is the 2D string theory, or C equals to 1 string theory, and its duality with matrix quantum mechanics. So two-dimensional theory that is dual to 0 plus 1-dimensional matrix quantum mechanics. Another example is 2D type 0b, type 0a, which are supersymmetric versions of them, also heterotic versions of them. Going up 1 in dimension, of course, we have ADS3 CFT2 strings. And another low-dimensional models that will play perhaps a slightly closer role to what we'll discuss later today is the minimal string and their duality with matrix integrals. So as opposed to the matrix quantum mechanics, there's no time in this one. It's just a 0 plus 0 matrix integral. in that sense. And even though this is a slightly different perspective, at least how we think about that we'll get into. Okay, so these are examples. Today we'll discuss another example of this. And before we get into the details, I'll just flash it what it is, what's the model. So this is it. So it's a string theory and that admits an exact worldsheet description in terms of the worldsheet CFT, which is the following. We'll describe this in detail, but this before we get into this is it. So we got Liouville CFT at central charge equals 25, and perhaps a not so familiar as ingredient here is Liouville CFT as well, but central charge less than or equal to 1. Sometimes goes by the name as timelike Liouville theory. Okay, so we'll describe what that is. And of course, you arrange the central charges such that these two add up to 26. Then once you couple them with a usual VCO system, then you get a critical string background. The exact worldsheet theory. Okay, so that's the model that we'll study today. Okay, but continuing. So just one word of perhaps a philosophical point, but as string theories, usually we discuss a worldsheet theory, which is what the ingredients I described in the previous slide. So it's a worldsheet CFT, it's a conformal field theory, even in this two-dimensional space. But of course, the thing that we're interested in at the end of the day is how this worldsheet string is embedded in space-time. So this is where the physics happens. The S matrix happens, and all those good things. So that's a typical thing that we do. And so the worldsheet, which is in here, is more of an auxiliary device from which we compute things. Okay, but however, I guess in part one of this talk, we'll actually pretend we actually don't care about the space. We don't know what this is, but just we'll use the ingredients of worldsheet CFT of the previous slides and interpret them as just as a model of quantum gravity in 2 dimensions. Okay, that's sort of the philosophy of how we're thinking about it. Okay, so in this context of low-dimensional 3D quantum gravity, this recently has been a surge of interest in this nearly pure theories of 2-dimensional quantum gravity. The most famous example, of course, is JT gravity.
Sorry,
yes.
but still we impose Virasoro constraint and everything.
Yeah.
So it will be stringy.
It is a string theory, yeah, in the usual sense. It's just that, for instance, this is not of that form, JT gravity, but the language that was used to describe what kind of observables we're computing would be closer to this type of model. But you're right, there's a fully string background. Okay. And at the end, we'll discuss a little bit about what's a target space that we can also discuss. Okay. So JT gravity, this is the actor for those who've not seen it. This is it. This is pretty simple. A theory of a metric, a 2D metric, and a dilaton, which with only this Einstein-Hilbert term multiplying the dilaton, and it's to integrate the dilaton, that this just restricts you to hyperbolic metrics, and then you're just left with some boundary action. Okay, so one important result in this literature was that it was discovered that this two-dimensional theory of gravity, a simple looking one, was discovered to be dual to a double-scale random matrix integral. Sometimes the interpretation, of course, is that somehow this 2D theory of gravity is not dual to a single quantum mechanical theory, but rather to an ensemble, random ensemble of matrices. Okay, so that's one difference. This is part of the context. Of course, matrix integrals, the relation between matrix integrals and string theories dates back to the 80s, precisely to double-scale matrix integrals, which take this form. So the partition function is you got a matrix H. I call it H because the interpretation, of course, is that somehow that's a quantum mechanical theory that is dual to the quantum gravity, but it's a matrix. Okay, and then it takes roughly this form, and you can reduce it by diagonalizing the matrix to just a n integrals over the eigenvalues. Okay, the main point is just that these theories have been studied quite a bit, and there's plenty of different techniques that are used to study them, like with Boolean polynomials, with equations, whatever. You can learn about that. But a particular limit that it's relevant for duality with string theory. It's the so-called double scaling limit, which we take the number of eigenvalues, so the size of the matrix would be infinity, while retaining a well-defined density of states of the eigenvalues themselves. And that depends on the potential. Okay, and the main upshot of this whole machinery is that it admits a genus expansion. For example, this so-called partition functions, in which just means introduce trace over the Hilbert space, and evaluate this matrix integral. They admit a timelike expansion that looks very stringy, sort of just weighted by the Euler number of the surface. And the beauty of this matrix integrals is that once you give me this density of states, then there's some powerful techniques that I can compute any of this genus G with n pointers observables. So once you give me some density of states, I can give you all this type of observables to any order in this perturbative expansion. Of course, this duality with 2D quantum gravity and minimal strengths, and then is what we'll study in here. Okay, so connecting the things that I was mentioning, so to the JT gravity with stringy and matrix integrals. So this is what we'll discuss today. So I'll discuss a new family of critical string theories, the ones that I described a couple of slides ago. There's a worldsheet CFT description, and then we'll see that it can be equivalently described by a matrix integral, just like in the previous slide, with this particular density of states, stage. And for those who like conformal field theory, this stage is something very natural. This, if you take the Virasoro vacuum character of a 2D CFT, you do a modular S transform, then you get this density. Something natural. But we'll have more to say about that in a little bit. But one thing that's nice is that with this, if you take a particular limit of this duality, they'll present where b goes to 0, in some sense a semi-classical limit. The central charge of Liouville CFT of the ingredients here go to infinity. Then it reduces to the JT gravity matrix integral duality of Sachs, Schenker, and Stanford. As we can see here, for example, if you take b to 0, then this one of the cinches linearizes, cancels the root e on the denominator, you just get this famous cinch root e.
In this case, the timelike Liouville has negative infinity. Is that correct?
Yeah, so in some way you can say that the Virasoro mutable string provides a stringy description of JT gravity, plus more stuff away from me. Okay, so that's one of the claims. And how we're going to do this is a little bit of a roadmap of what we'll touch upon during the talk. First, we'll discuss the worldsheet CFT, which is perhaps the most direct description of this theory, and then how this makes a stringent realization of a particular JT-like theory to the gravity. And to get to the matrix integral, we'll have a small interlude of how these two are connected via some machinery that was recently developed on 3D gravity, and how this gives a nice connection to the matrix integral description of the model. So this is sort of the roadmap. Okay, so let's get started. So we'll begin with the most direct, which is the worldsheet description. Okay, so yeah, one more word about motivation is just so closer to JT gravity. So in particular, one can study the Virasoro minimal string, at least classically, can have this description in terms of a similar action like JT, but with instead of having the linear potential for dilaton, let's get a cinch potential written down here. Okay. So why is this related? So, well, as you can tell, just from the classical action, if you take b to 0, it's just JT. But then if you do this, the following pure definition, so going from the metric and the dilaton.
Sorry,
Yes.
you have the the hyperbolic sign because you have the exponential both for the space life and the time like Liouville. That's why you have.
Well, I'll show you the next slide that hopefully will be complete. From this perspective, it's almost yes, but not quite. You have to do this field redefinition to see it. So if we do this field redefinition from the metric or like the mile factor here, so these are the two variables defined here, so just a linear combination of them. You do the field redefinition, you'll land on this action. Two decoupled actions. Well, Liouville theory, which perhaps might be familiar to some of y'all on top, but also this time like Liouville theory.
Okay, that's my question. So you relate the two cosmological constants in this way.
Yeah, so in particular, if you do that classical manipulation, you get this smaller constants, and all these things are related in this perspective.
So a priori, there is no reason why to tune the two cosmological constants, right?
Yeah.
So you could have a different W.
Yeah, it's because you're right. It originated from that tinge, which is smart coupled together.
You show again the field redefinition.
Yeah.
There is a type. Pi is equal to minus chi.
Pi equals to what?
Pi is equal to minus chi.
Sorry, where? Pi equals to minus.
Yeah, because phi, if you change this, you not multiply by, if you change the sign of phi, you get chi. But that's
Okay.
It's just
there should be some relative sign.
Yeah, you're right.
HEP inverse.
Okay, maybe don't trust the exact signs of this one. There's. I thought I checked this. Okay, anyway, something like this lands you in
Something that
some permutation of signs lands you in this one. Okay. The main point is that okay, this was maybe a motivational thing, but of course we're not going to use these classical actions. We'll use the full boost resolution, which luckily for us, it's available, and we don't have to do anything perturbative in this sort of actions. We can just do it non-perturbative with the CFTs.
Can you also study the case when mu TL is not related to mu L as Tom was saying?
Yeah, I think in principle, if your starting point is just a CFT, yes.
You can study that. And what do you get? Like, do you get something? Some
yeah,
dual, some. You get some count, like some
in case. I'm not sure to be honest.
It's not technically, it's more hard to do that, right?
I don't think it would be that the techniques would be exactly the same. It's just I don't know what the interpretation is actually. So maybe let's discuss that after talk. Because that's a confusing part actually. And I'm mostly confused about because of the target space. But okay, so during that, with this particular model, okay, let me write it again. It's this worldsheet CFT, timelike Liouville. So just to put a little bit more context, so this is sort of like the weird ingredient. So this Liouville piece is perhaps familiar. So if you change this timelike one with a minimal model, this is called the minimal string. If you change it by just a free boson, the timelike signature, this is just equal one string. Okay, but today we'll consider this a slightly more complicated ingredient, which is timelike. Okay, but before we get into that weird one, let's discuss the familiar one, just space-like, or just ordinary unitary Liouville CFT. So the center charge is parameterized in this way: 1 plus 6 b plus b inverse squared. B is some parameter, will be a parameter of all this family of theories, and it can be taken to be from 0 to 1. Okay, so this CFT is not compact, so it comes in a continuum of its primary states come in a continuum, but it's unitary. So for example, the operating spectrum is just scalar Virasoro primaries with this weight. There's some constant plus p squared. P usually we call it the Liouville momentum, like this. There's just some real variables. Sure. And the 3-point functions. So the other sort of important data for cosmological theory is 3-point coefficients, OP coefficients. It's a complicated formula. It's known as the DOCC formula, but it's a very explicit formula. We know a lot about it, and for all, I won't write it down because it wouldn't be illuminating, but it's known and it's explicit. Okay. And with this pieces of data, in a 2D CFT, we can compute anything we want in principle is this. So 4-point functions, 5-point functions on any Riemann surface with any number of handles and things or boundary. We can, sorry, not with boundaries, but we can compute any of those, at least in principle. Okay, so this is a familiar one, but how about this one? So this time the Liouville is it's a bit funnier. Just naively, you would think it's, if you want to go to a regime in which the central charge is less than or equal to 1, you would think that you just need to take B to be imaginary. Okay, that's true. Except if you analytically continue the DOC formula that I presented in the previous slide, then this fails. It's just you cannot do this. Okay. However,
What thing takes that?
yeah. So for example, well, I didn't write the formula for the UCC formula, but that 3-point function, if you just naively continue it, it blows up precisely in this branch. And yeah, so all your correlation functions are just infinity. However, there's a distinct solution precisely that makes sense along this branch, this imaginary branch. Okay. So it's still not compact. It comes in a continuum. It's not unitary, which is kind of like a maybe funny part, but it's only a really mild non-unitary. The non-unitary is, you know, one way to see it is that with C less than or equal to 1, this could be negative. So it's a little bit, you know, violent and unitary bound, but it's only small. Okay, then P hat. I'll put hats on everything that's timelike Liouville, just to distinguish from the space-like one. But it's still labeled by some real momentum. Okay, and again, the DOCC, its associated 3-point function has also been bootstrapped. It's another solution to the crossing equations, and it's different. So let me call it hat. But in some convention, it turns out that it can be written as the inverse of the previous one. So it sounds. Oh, so just keep in mind that it's a distinct function, but it's related to the other one. In some nice convention, it looks like this. Okay. Okay, so that's.
This fixes the normalization of the vertices, right?
Yeah. So I chose a particular factors of P1, anything that is factorized functions of P1, P2, and P3, you can reabsorb into this.
Yes. So
vertex
you
number.
lose this.
Yeah.
You don't have this freedom any longer.
Yeah, exactly. So that's no longer our freedom. So now.
What do you mean by nice convention? You just mean normalization of the operator?
Yeah. Otherwise, you'll get some extra factors.
So this violation of unitarity, it's not a problem for the target space interpretation?
I mean,
Because
I
you
wouldn't
have
say a
negative,
problem. I would say a feature.
but for what, how do you interpret negative norm states?
Yeah, we'll come to that. We'll come to that. But hold on to a question, but you'll have to hold on to like maybe 30 minutes. Okay.
Sorry, the normalization that you did here, what
Yeah.
does that do to the 2-point function?
Right. So if the 2-point function, this normalization, in this convention, the 2-point function will be a delta function, P1 minus P2, divided by P1. If the other, perhaps more conventional DOCC, if you look at cosmological papers, that convention you wouldn't get that. You will get without the P at the bottom, roughly speaking. But it also shows up in there. So that's a choice.
This formula can be derived following from the Teichner trick.
That's how it's derived. But notice it's a distinct solution. It's not the continuation of the other.
Yes.
Okay, so now, that was just at the level of the CFT. But if we want to make this a string background, we have to combine all these ingredients. And the Arshel vertex operator, the physical stuff, it's a combination of the 2 ingredients. But it turns out that to make it physical, the usual condition that the conformal always has to add up to 1, sets this p hat to be the imaginary value of this space icon. Well, you have to make sure that it's okay to do that. It's pretty detailed, but it turns out that this is a pretty trivial thing to do for this second DOCC formula. You can do it, and it's perfectly well defined. But yeah, that's the point, that physical state condition imposes that p hat is actually the imaginary piece of the other. Okay. And one of the observables of this string theory, like string amplitudes, is like correlation functions of these two ingredients, integrated over a moduli space of your given Riemann surface. We're going to use a picture. This is there's two punctures if you want, and there's two genus 2 surface. And I'll be drawing these pictures a little bit more like the JT ones, in which there's like a G of p-sig length. We want to use that language. P is what the length is. It's a length, not a momentum in this case. It's the length of this red ones. Okay, and this amplitudes in the string theory language would be volumes of this surface. So in the b equal to 0 limit, it really are just the volumes of 2D Riemann surfaces. For non-zero b, it's some sort of quantum analog of that. And I'll be using that language. Those volumes is what we call the v, and p's are roughly speaking lengths.
So P here are real, right?
Yeah, they're right.
So then you're going outside the spectrum operator described by the timelike Liouville.
Well,
Or
yes,
or
yeah. So that's the comment that I said, that you have to make sure that continuing the time level ones to imaginary. It's okay to do, and it is. I can show you.
And is why you make that choice instead of doing that for the physical Liouville part?
That's for convenience, because if you try to do the same thing to continue the space-like one to imaginary one, it's a lot more complicated, because then you have to follow it and it might cross the contour poles, and it's a different monster. So that one is actually just for convenience. Like I said, time of movement is pretty trivial to do. Nothing changes, nothing crosses contours.
But is it a part of
however,
the definition of the theory?
Yeah, I think it's a feature of just the description in terms of this 2 CFT. At the end of the day, though, once we have the expression for this, there will be a duality that it changes the 2 CFTs. But that's the level of the intermediate region CFTs is actually not very apparent. It's only after you integrate one. Good, yeah.
Isn't what you're doing also more analogous to what you do in a standard personic string theory, right? Take the Euclidean worldsheet option and take the momentum.
Yeah, but in this case, I chose one, right? And
you chose the time.
I chose a convenient one. But at the end of it, what's interesting is that these two ingredients are very different looking. But at the end of the day, once you compute these volumes, there's still the symmetry of whether you can change the what we call timelike with space-like, which is kind of funny. It's somehow expected, but from the intermediate pieces, these two ingredients look completely different. Okay. So in particular, this volumes also don't really behave like an S matrix. Turns out that we'll see they're actually just polynomials, which is kind of silly. So they really don't have like factorization properties and all those things.
So how we should think of what is the meaning of it?
Yeah, so this is what I'm saying. There's a better meaning. It's like an actual volume of this, where the p's are just lengths. And it does become precise in the v equal to 0 limit, which it reduces to the Peterson volumes, to the given surfaces. But for general v, we call this a quantum analog of those. Okay.
Just to see if I understand. In the case of the 2 3-point function, this is pretty obvious that we simplify because of what you said. One is the inverse of the other. Right? But what you're saying here is that this kind of the fact that the timelike is sort of the inverse of the space-like is more general, and it's not only working for the 3-point function of the sphere, but also that's the point.
Yeah, roughly speaking, but as you mentioned, beyond the 3-point function, it's completely non-obvious that this happens, or that there's anything.
You can rephrase this saying that this inverse between the relation between the space-like and the timelike seems to work.
Only after you, only at the end of the day, after you do the complicated integral and modular space and so on, roughly speaking.
So, but when you say that these are volumes, these volumes are Euclidean signature volumes.
Yeah.
So because usually physical observables are in the Minkowski signature, the S matrix.
That's right. Yeah. So for this part of the talk, I'm forgetting the target space, which will be Lorentzian. All right. This is just a Euclidean theory. It's at least some string theory prescriptions compute this observable, which we call volumes, but they're Euclidean. Okay. I guess it's we'll discuss the target space later. This is what Gaston was referring to, that of course the 3-point function and the conventions that I chose, there's no moduli to integrate over or anything like that, so it's just a product of the the 3-point functions, and in the convention that I chose, this is just the inverse of that. So it just cancels it, it's just 1. But this is just a conventional thing. Okay? So the special thing is that even though these are two complicated functions, they cancel each other out. However, with the 4-point function, they do not, or not as obviously. So now this is not just there's a non-trivial integral that you have to do, and let me just like scare you with this a little bit. So there's the remaining moduli is an integral over C of the complex plane, and you have to evaluate a 4-point function in individual CFTs. And now we don't know how to do other than expanding the conformal blocks, as in this picture.
So yeah, but the conformal block of each case satisfy kind of BP-seed equation.
Yeah.
Can you see that the BP-seed equation on one and the other one is one sort of the inverse of the other?
Not really. Not really. There's a special property that we'll come back to a little bit, and we'll discuss 3D gravity, which maybe it will be a way to try to find this kind of relationship, but at this level, no. So now with this, don't cancel each other out. Of course, you know, for instance, you have to do this integral first before anything cancels. Nothing cancels here. Nevertheless, if you can compute it numerically, at least in this case, if you had some intuition of why this could be a simple thing. And okay, so this is just to say that you can numerically check that it actually is just this polynomial, which sounds kind of silly. This is a quadratic polynomial, also this is quadratic. Okay.
So it does not depend on B.
Sorry, it does. So C depends on B.
C is the one.
C is 1 plus 6 equals B equals 1. In a simple way as well. Okay. So so this is kind of silly. These are complicated functions. You can also evaluate the towards 1 point. It's another simple-ish one that you can evaluate. So they're like absurdly simple. They're just polynomials. So there has to be some other way of explaining why this is happening. Okay. Well, again, it's just observation again. So this, if you take the B go to 0 limit, you reduce to the Weil-Pearson volume. And if you follow the JT gravity literature, then these are the ones that reduce it. Okay. So
Does this simple formula show up with other examples of worldsheet CFTs? Because it sounds like there should be a clever way to describe this product theory on a worldsheet with timelike together with spacetime, which will make manifest that you know the integral over the modular space between such formula.
well, there's some way, but it's convoluted, which is using this 3D gravity stuff. But
theoretically,
you're right, there are other examples of low dimension string theory that have a little complicated and end up giving you something dumb or simple, not dumb. For instance, equals 1 string theory in this case, except there's a bit more structure. There's this continuity system because there is a good old S matrix. It has a little bit more structure.
So ADS3 crosses 3 superstrings for EPS states.
So those are examples, but somehow this feels a little different. It's just polynomial, but there's no even this continuity and factorization things. So it seems even simpler somehow. Okay, so this is what we described so far. This is worldsheet CFTs, perhaps familiar to most of us. And if you like to think about it as incidental to gravity, it's a stringy realization of that. Now we'll discuss how to get to the matrix integral. And for that, we'll take a short detour to 3D gravity. Okay, which is based on some recent work by Collier, Eberhard, and Chang last year, in which they were studying partition functions of 3D gravity. The whole point there was to to define a specific Hilbert space for a given geometry of the 3D manifold in question. That's topology. So for the case relevant to today, it will be of this particular topology of the Riemann surface, 2D Riemann surface times a circle. Okay. So the Hilbert space that they proposed, and it was also based on earlier work by Belinde and many people, including for example Roddy here. The Hilbert space, the claim is that it's just composed of Virasoro conformal blocks. Okay, it's a funny thing to do, but in addition to this Hilbert space, you can define an inner product between these states, between conformal blocks, in the following way. So you give me a conformal block, you give me another conformal block, and what you do, this is the main content of the paper of Collier, and Shang, is to evaluate this inner product. So what the inner product looks like is you give me this conformal block, which is a state of my Hilbert space, this other conformal block, which is a different state. The prescription is to multiply it by an appropriate timelike Liouville CFT correlation function and VC ghosts, which come along for the right. This is some auxiliary thing for now. And you integrate not over moduli space, but rather on timelike space.
This is the chiral half.
This is the chiral half, yes, yes. For the actual 3D gravity, the full theory will be the Hilbert space times. That's a other chiral half. But the one that is relevant.
Divergences also.
Sorry?
There will be divergences.
Yes, of course, of course. This is some of these evaluations are actually divergent. But for the one, actually this one is too, but it's some formal manipulation that we'll do in the next slide that we'll get there. But yes, this is only the chiral half is the one for 3D gravity point of view. Okay, and the main point is that this looks very similar to what we're trying to compute over here, except this integrated with something else. And also, crucially, you're not integrating this both are supposed to be intermediate Liouville momentum. So in a correlation function, we integrate over those, right? But this one, you're not supposed to do that, but then you're supposed to integrate over the timelike space. The timelike space is like for instance, just to put things in a simple example, think about the torus 1 point, whose moduli space is just the fundamental domain of Liouville. The timelike space is just you unfold the mapping class group, so it's just like the upper half plane. Okay. So it looks very similar to the string theory computation, but it's not quite there yet. But we can rephrase the problem by evaluating the actual partition function. So just trace over this Hilbert space of conformal blocks. In this way, you can interpret it as the partition function of a chiral 3D gravity on this particular type of topology. And what you're supposed to do is trace over the Hilbert space of conformal blocks, roughly this way. Now you do integrate, by doing this trace, you also integrate over the intermediate momentum. Okay, now it's starting to become a little bit more like what we usually do in CFT. Okay, now it becomes a correlation function because we're integrating over the intermediate momentum. And now it's like this. It's still a bit timelike space, but then since we're doing a 3D gravity partition function, we're supposed to divide by the mapping class group of topology, which in this case is just a one of the 2D surfaces. Of course, so this is the point. This is a bit formal because this is an infinite integral and this is an infinite volume, generically speaking, an infinite volume group. But by definition, the timelike space divided by the mapping class group is just a moduli space. So then you get this formal relation that the amplitudes that we were computing in this Virasoro minimal string can be phrased as just evaluating this partition function of this particular chiral UV gravity. Right? So we just translated the problem, but
So why you actually integrate over Tech-Muller? Because for the chiral half of gravity, you would think that you have to impose also that if a function is invariant under global diffeomorphism, that will give a particular global diffeomorphism that act at fixed time on an initial surface. If you have, and that would require to factor out the modular transformation mapping class group. I mean, in the example of Witten and also in what we did 9 years ago, right? We complete gravity, we had 2 copies of Tech-Muller space, but we divided by a single copy of the modular group. And what Maloney did, right, for chiral half, he had actually integral over modular space, but instead here you have an integral over.
In other words, is it clear that it's not the same as integrating on the model space and divided not by the entire MGC, but by the volume of the conformal clean group?
well, in this particular case, for this poly, it is, right? This is, for instance, towards one point, this is just SO2C.
Modulus.
Yeah. So in that case, it is.
So can I see the previous transparency?
Yeah.
Yeah, even here, I mean, why is the technical space? Why shouldn't you impose that, say, Gauss law, right? Or if you want, some of the constraints tell you that the wave functions are invariant under the mapping class group.
Yeah. Well, the thing is, like, for instance, let me just say that if we're okay with just taking Virasoro conformal blocks as a state, so okay, so then okay, why integrate? Let's decide what to integrate over. You said moduli space, and the thing is, like, conformal blocks are not invariant under what's it, the mapping class group that you divide by to get the moduli space. But for instance, if you do for instance, just to put it more concretely, if you do the fundamental domain and you do apply a T transformation, these things are not invariant under that. So your inner product, at least defined with the integral moduli space, will be ambiguous. So that's one practical
Wouldn't
reason.
that tell you that you are taking a scalar product of wave functions that don't satisfy the constraints, I mean, the different mapping constraints?
Okay. You then the complaint would be about the Hilbert space, right? You'd be like, that's
Yeah.
not the correct Hilbert space. That I don't have a good answer for, but this is the claim at least. But once you accept that the Hilbert has to be this, is mostly like the thing that would make most sense to do if you just have conformal blocks.
Yeah, I mean, what has this to do with gravity and
Sure.
clear?
Yeah, it is admittedly a funky theory of gravity. Right? But today though, it's like we won't dwell too much on the 3D gravity of what the interpretation is. The main message here is just that, okay, we know that computing this is hard, and the question is do we just translate the problem? Is there an easier way to compute this? Yeah, the answer of course is yes. And this luckily was also already computed in an earlier paper by Lawrence Eberhard in 22. Using some techniques of intersection theory on Riemann surfaces. It has some expression like this, turns out, in terms of this funny homology classes. And the main point though is that there's some very well developed machinery to just actually compute this integral. Okay, well that makes it almost immediate to compute this.
Is it all of this? How do you define it? Because you have an infinite dimensional mapping class group, right?
Yeah.
So you have an infinite integral over technical space.
Yeah.
And you
Yeah. So this is
infinite over
this is
infinite,
this is true. This is the physics derivation that we divided something infinite. So we have something infinite, the integral of technical space, and divided by something that is also infinite.
because this volume are volumes of the moduli space. If it was a volume on technical space, it would all be divergent.
Yeah.
So
if you want, this is an educated guess. It is true that we didn't derive it mathematically. You didn't provide a mathematical proof.
but what's the point of giving bad derivations of a non-interesting theory? I mean, this is the thing that matters, right? It's V.
Yeah. Well, at least it will
Whatever
give
they
you
mean.
an efficient way to compute these volumes.
And these volumes again are in the limit b going to infinity become the volumes on on Riemann surfaces with boundaries.
Okay. Yeah. And of course, like the main point is that you can then massage this to the topological recursion of matrix integrals. There, then you close the link.
For any b.
For any b, yes. Which of course includes the JT gravity case. B goes to.
So in the relation, the Mizrahi relations are for large b or for any b?
So we have one for any b.
Yes, the ones that.
The ones for what for if you want b equal to 0. Okay. Well, I'm
Sorry, so the previous formula, does it immediately follow from the previous formula, the volume we get will be for non-SCP?
Yeah, for example. Yeah. Because the p dependence is just
It's from the cosmological class.
yeah. You just expand this and obtain the
That's right.
and then so it's just you can immediately see that it's a polynomial and that p squares. Okay. So this makes some properties obvious. But getting there, of course, is not obvious.
By n bar, you mean some compactification?
Yeah, of the modular space.
Is that in Mumford? Is it something else?
The Mumford compactification. Yeah, this is the usual one. Yeah. Well, from the the amplitudes, the string theory scattering amplitudes, it actually doesn't matter because they're convergent integrals anyway. But from this language, yeah.
It sounds like one would want to cook up, but if you want to understand it from a worldsheet perspective, one would want to cook up two-dimensional worldsheet CFT. The scoring function will give you this insight
Directly.
Yeah.
Instead of like
exactly
factorized. Yeah, that maybe that's possible. I don't know the answer to that. This is and yeah, okay. So in the language of JT gravity again, so you get this what we would normally call the dispartition function and the trumpet partition function. Turns out that these are just given by the vacuum Virasoro character and the non-degenerate Virasoro character with momentum p. Okay, so one, for example, the top one, think about it is just a disk. The partition function is just a partition function of the solid torus, the disk times the solid disk times S1. So just a solid torus. So then from theory of gravity, we can just say that we can just deduce that it's just a vacuum character in CFT. Okay, so just a quick trick. And using this trumpet, for example, if you remember from Sachenko-Zephyr, we of course can glue in trumpets to the geodesic boundaries here to make them asymptotic boundaries. The gluing measure is the same one as in JT, just 2 PdP. And with this factor of the trumpet partition function, and then you glue them into the volume itself. In this picture. Okay, so that will close the loop to the matrix interval. Okay, which we started talking about. And what I told you before is in this double scaling limits of random matrix integrals, if you specify to me the density states, then you essentially specify everything in the theory by this topological recursion. Okay, and this is the formula, and of course it reduces to JT, for example, and so on. And this again is the comment that for those who like 2D CFT, this is just the S transform of the vacuum character. And of course, this is the dispartition function. You just take this Laplace transform. You also get this this density states. Okay, so this specifies the whole thing. And I'll be a little quick in the interest of time, but of course, this is if you're more comfortable with matrix integrals rather than, for example, intersection theory or something. You can of course phrase it in terms of resolvents or whatever your favorite observable is in matrix integrals, and they of course obey a recursion relation for themselves. And these are all related by different Laplace transforms. Okay, so this is summarizing that you can choose your favorite type of observable. Here are like the string amplitudes if you want that we started with. The partition functions that you get by just gluing these trumpets. Or you can talk about the resolvents, which is perhaps the one we're more used to when we discuss matrix integrals. But there's just an inverse Laplace transform, a specific Laplace transform of each of them to get to your favorite one. Okay, so for example, here's a topological recursion straight for the volumes themselves. This is the analog of Mircea-Kane's recursion relation, but now it's it depends on B. So for example, there's for generic B. Again, if you take the B equal to zero limit, you reduce to the one that Mircea-Kane's wrote down. So it takes this formula. Perhaps it's not super illuminating to just look at this formula, but of course the point is that well, it's an explicit formula. For example, I showed you how to compute this, and we saw that it was a fairly nasty thing to compute. By using topological recursion, for example, we can compute something, well, one compute this, for example, using the previous recursion. You can code it up in Mathematica and you can compute this thing, which would be nearly impossible from a direct calculation. Okay. In the interest of time, I won't discuss non-perturbative effects, which involve CC instantons, but I'll just tell you that, of course, you can also analyze non-perturbative effects that go beyond the topological recursion perturbative results that we discussed earlier, and you can match those to string theory on the direct worldsheet string theory by D instantons. This involves knowing a little bit of boundary component theory, CC branes and FCCT branes. In this case, CC boundary conditions. And the timelike Liouville ones, I just want to mention that it's slightly different. Just has this something called half CC boundary conditions. I want to mention it just to say that boundary component field theory of timelike Liouville theory is still very much underdeveloped. And using, roughly speaking, we back engineer what this should be the correct ones just to match to the non-perturbative effects of matrices. This gives us a way to understand boundary component field theory in timelike Liouville through this. Okay, but then you can match the string theory side and the matrix integral side, also non-perturbative, at least at this order. Okay, so in the last 5 or so minutes, I just want to discuss if there's any target spacetime interpretation, going back to string theory, that usually that's our main interest. Okay, and this is a little more open-ended. Okay, so back to the picture. The most we can describe the perspective from this side to quantum gravity, but our interest is usually the physics in target spacetime. Okay, but for that, just to build some intuition, I'll do a short interlude and just put all 2D is equal to 1 string theory, just to see how we usually think about it in target spacetime. So it's simpler. So we still have this usual space-like Liouville CFT, and then we have this time-like free boson. No time-like Liouville, it's just a free boson. Okay. Now we come back to perhaps Sergey's question from half an hour ago. So here, so we combine again the ingredients, space-like Liouville CFT with the time-like free boson piece. And the way we think about it is still a Lorentzian picture because it's a time-like signature free boson. So its weight, the Onshore condition, has a minus sign. That's the whole point. And so it has a Lorentzian dispersion relation of a massless field. So that's what we think of massless particles in space-time. Okay, but how does space-time look like? So this is Liouville theory. This is the action, worldsheet action again. So the way to think about it is that if you remember the string coupling, it's controlled by whatever multiplies the Ricci scalar, 2 to Ricci scalar. But since that's a field, and the field is interpreted as a dimension in the target space-time, that means that on one hand side we have very weak coupling, here when phi is large and negative, or very strong coupling, phi is large and positive. But then the Liouville potential, the third term in the action, shields the potentially uncontrolled region of space-time like this. Okay, and then the onshore states are just massless states that come in, interact here with the string coupling is non-zero, non-vanishing, then bounce off this potential wall and then go back to the asymptotic region. So that's how we think about 2D string theory, sequel function theory. Of course,
in sequel 1,
yeah.
you have a different operator, which is phi times the exponential of phi.
Well, in the convention I wrote, it's usually this.
In that case, yes, but
Yeah.
when b is 1, namely c is 1,
Yeah.
apart from the exponential field, you have an extra one, which is phi times the exponential of phi. This is not primary here, but it's primary when c is equal to 1.
Oh, you mean that you can further reform by that?
So when b is 1, that is to say when the center of charge is 25,
Yeah.
You have a competing operator, which is phi times the exponential of b equal to 5.
Yeah, maybe you can deform that. That operator is logarithmic, so it's I'm not saying that's bad, but it's a further feature one.
No, it's not. It's logarithmic for
Yeah.
b different from 1. It's not logarithmic for b.
Okay.
It's primary.
Okay, actually, I wasn't aware of this. Well, this is the one that, at least I understand, that this is the one that's dual to the major quantum mechanics. One can further reform, and I don't know the answer what happens when it gets down. Interesting to
But
see.
are you going to be into B.1 or?
I will be, yeah. Yeah. But unfortunately, the fact is we don't use this action at all. Use the bootstrap, right? Okay, but that's at least the physics of this target space physics of this model. Okay, then this actually does have a conventional S matrix. So you have in-states and out-states. You can compute them using string perturbation theory. Here are some examples of what the S matrix elements look like. Also pretty simple. Just polynomials, I guess, and the external items. They have some more interesting features. Okay, this is not that interesting, but it's got some imaginary p's, which you can understand as coming from a factorization or discontinuity in the amplitude. But okay, so back to timelike Liouville. A potential interpretation of this is out of a time-dependent background. And so let's review why that is. So the main point that we do in the Virasoro minimal string like is to replace the timelike boson with t equal to 1 Liouville CFT. Timelike. Okay. Now remember the initial condition that we had to continue one of the momenta to be imaginary. In this case, it's a natural interpretation of that is the same as in c equals 1. That we want a dispersion, so we read this to make 1,1. The dispersion relation we get is also Lorentzian form. So demand this 1,1, you get this dispersion relation. The ones cancel and you get massless dispersion relation. So it's still a scalar, massless scalar 1 plus 1 dimension. Okay, but now let's do the sort of similar analysis just to get the intuition. So this is the usual Liouville action. So the first step to get to timeline is to continue to this branch of imaginary B. Yeah, so this intermediate step is that one simplifying feature of being precisely B equal to 1 is that the linear dilaton piece of this timelike piece is 0. So in particular, the string coupling is independent of time. You can relax that, but this is some simplifying feature, one thing less to worry about, at least. But then you do you want to go to timelike signature, so you rotate in field space to get to the timelike signature. Right? Now, if you follow what happened to the potential, it became an exponential potential like this. But since it's of the timelike signature, this is the field that we interpret as the time coordinated space time. Okay. So what's the picture? So we have the usual Liouville wall. This is the space-like one. This is 2D string theory. And then we have the time-dependent potential, like here in blue. Grows in the infinite past and the dimension that I chose.
You can put it in the future. So.
You can, yeah. But I chose this one. Like to think that the universe is created rather than destroyed. But that's a choice.
You're happy people.
Yeah. And some of the amplitudes that you compute in string theory look like this. And the interpretation I want to pursue is that it is of a cosmological wave function, components of a cosmological wave function. So we have some initial state that is prescribed by the worldsheet CFT. The specific worldsheet CFT gives me this state, and I can probe it by computing scattering amplitudes in string theory with where the insertions are these massless vertex operators. Where the potential vanishes and we're back into this equal to 1 vacuum, time independent. Right? So just this last comment about like what the actual string diagrams compute from a space-time point of view. Well, just the combinatorics work out. Combinatorics is a disconnected diagram, so a little bit similar like the instantons. Disconnected diagrams like this, for example, in the 3-point function, you can have the 3-point or the 2 points into the 1 point, all weighted by the appropriate genus, Eastern. And the comment I wanted to make is that this seemed to organize in a nice way like this. So you can, the combinatorics are reproduced by this sort of wave function that's written here. First one, just a 2-point function, is what we might recognize as a squeeze state. And then the next, all the G string corrections that come from like the higher point amplitude. So in this sense, is what I was saying, that you can, by probing the initial state with perturbative states in the future, you can reconstruct, if you're powerful enough to beat all these things, the initial wave function. Okay. So let's take a step back. So we mostly discussed this perspective of the Virasoro available string as a theory of quantum gravity, as a quantum version of String's built on gravity. And we solve it is through some roundabout way that I described it, that is dual to a matrix integral. Particularly has no time, it's just a matrix integral, random matrix. However, from the target space point of view, if you're interested in space and physics, to me at least it seems like it lives in the same world as 2D string theory. Perhaps with some deformation, of course, it's a large one because it's timelike Liouville theory. But to me, this suggests that it also has to have a description in terms of matrix quantum mechanics that describes the space-time physics. So that's of course, that's a question mark right there, right? We don't know that yet. This for sure we know is true. Just showed it. But to me, this gives me hope of at least one example, even though a little bit contrived, but an example in which time perhaps is emergent in some way. So somehow we go from the matrix integral that has no time, and then time emerges somehow in this string theory model. But I don't have any more concrete things to say at the moment. So let me just almost end here just with some future directions. Some of them I briefly mentioned, for example, directly in the Virasoro minimal string. Of course, boundary component field theory and timelike Liouville theory, there's still much work to do. Of course, some generalizations to consider supersymmetric versions of such, which might lead to a effective potential that is stable in that case. Another one that is work in progress is, instead of coupling timelike Liouville CFT and spacetime Liouville CFT, you can just couple two spacetime Liouville CFTs. Of course, these have to be necessarily a complex central charge, so that you can get a vertical system with central charge 2.6. But now in this case, now the special thing about timelike and spacelike is that, roughly speaking, at least a level of 3.5 they cancel some way. In this case, it just does not. It does not cancel at all. There's something complicated and something also complicated, still complicated. Nevertheless, it has some nice structure. As this parameter b, and also labeled by some parameter b. And for example, the 3-point string scattering amplitude has very nice elliptic structure in terms of this b squared parameter. That was already noticed by Bella Logica, and in the specific case in which this underchart has this value, there has been some recent search of interest with possible connections with considered gravity. So consider JT gravity, for example, but of course from this perspective, a bit more for full family of B, as it was in the first one of the string. And of course, from the starting space point of view, this is perhaps an example of holographic duality in time-dependent backgrounds, which would be, of course, very interesting to continue studying. So with this, let me open up for questions.
So, what is how many physical states you have in space-time in this case? Just the massless one?
Yeah, that's it actually. It's very special to 2 dimensions.
And could you write an effective action in target space? I mean, it's a 2-dimensional thing. So what is it?
Yeah, so it's not very special, but without the usual 2D string, the equal to 1 string, which there's no time-dependent potential, just time independent. That one we can write it down and just by matching, for example, and it's not very illuminating. It's just a massless particle, 2D particle with some cubic interactions, Schwartz interaction, and so on and so forth.
And gravity.
No, actually, there's no gravity. There's no dynamical graviton. Just because you're in 2 dimensions.
But there is gravity, right? I mean, is there a constraint that follows from?
That's a much interesting question. Presumably yes, but they're not very. It's not so easy to see where they're coming from. Because one way to derive the space effective action is through matching, but perhaps that's not so interesting. But the other way is through the matrix quantum mechanics, the dual. So there's a semi-long dance to go from the matrix quantum mechanics down to an effective. It's usually called the collective field theory. And in this procedure, at least I don't know what would be the constraints that come from even from what would be the graviton from the string theory point of view. They're not as strong because these are somehow discrete constraints. The graviton is not dynamical.
Still, the gravity is not dynamical, but when you impose the equations for motion of the graviton, you do get constraint.
Yeah.
Any theory of gravity in any dimension.
It's true. Except I don't know how to do it in the string theory language. Maybe that's, yeah.
But if you know a few interactions, the spectrum,
Yeah.
then you know that your theory will have general covariance. It shouldn't be possible to write down in concepts. Or at least to check that, I don't know, the action maybe is local or non-local, I don't know. It's a very basic property.
Yeah, it's a good question, and unfortunately I don't have the answer. What I can tell you is that, well, the effective action is local, just because it's a low energy effective action. But more than that, yeah, I don't have a good answer.
But what is the relation, if there is any, between the Virasoro minimum strain and the usual minimum strain?
That's I don't think anyone knows, but I mean, it's not hard to maybe imagine that there could be doing some analytic continuation of even just at the level of CFT, but I'm not sure. You can maybe conjecture that there's some way to go from the time level of CFT to a particular, somehow localized to a particular minimal model. I'm not sure, but it definitely seems possible because it follows the same. In fact, some computations that cosmological did back in the 1990s, 80s, to compute things in minimal string theory involved this timelike UCC formula, continuing from there. It doesn't sound crazy, but I don't think anyone really knows what.
But it's true that if I take the B to be the center, to be such that the center charge of the non-unitary minimum model, it will have a different three-point function than the one given by the formula.
But it could be that somehow you can extract it from it. That might be the case, but I don't know.
Does the 1/c, this formula for time like Liouville also have like singularities for special values of B?
Sorry, the timelike Liouville?
Yeah.
The DOCC?
Yeah.
Yeah, it has holes and so on. That's something that I actually didn't discuss, but it does.
But nothing in the domain where you consider.
Oh, you mean in B?
Yeah.
In
Yeah.
the B plane.
Yeah.
Yeah, actually, so I think maybe at the level of the 3-point function it doesn't matter, but for instance, the 4-point function you already run into problems. You can ask the question of like starting at this branch of the imaginary B. Can you continue away with complex B? The answer is no, because 4-point function starts to diverge.
Yes.
That's kind of good, right? Otherwise, at some random complex value B, you think you get two different DMCCs, the one, the usual one, and the timelike one, but that actually doesn't happen. So that's kind of good.
In the second part, you had this interpretation, space-time interpretation for the model, but it was only for B equals 1. Right?
Yeah, that's the one I've thought about.
Yeah. Why can't you do that for B?
I think you can. It's just that one feature is that the string coupling now is also time dependent. That's really the only reason I was like that move.
Because the linear level.
Yeah.
Is it imaginary, the coefficient? Like Q?
No, I don't think so actually. I think it's like no, I just
I probably missed the last logical step, but you said that the quantum volume can be determined by this Virasoro equation relation systematically even for higher genus set.
Yeah.
Then that was possible because of this interpretation that the quantum volume can be obtained by the partition function of really has higher gravity.
Yeah, that was sort of like, yeah.
And that this topological recursion relation is applied to this 3D partition function of gravity, and that's why you mentioned this flow through this 3D kind of gravity. Because I just tried to understand why this topological recursion relation works.
Yeah. No. So the 3D gravity interlude was just to make it a little more direct connection. But you can take a more simplistic point of view. It's like I gave you the density of states, and a matrix integral has its own topological recursion. And that's it. You don't need to talk about 3D gravity. But the 3D gravity gives you why somehow. Why? Because the topological recursion matrix integral, you can map it to both the Mirza-Kanye relation, also dependent on 3D gravity, but also to this index presentation of the volumes, which involve the 3D gravity presentation. There's a way to close the circle if you want, but
and one big last question is this works well for finite B, but if you try to stick to the JT gravity, like you mentioned that B goes to infinite limit, then in this picture it means that you have to do with timelike Liouville CFT with negative infinite C and Liouville CFT with infinite C. So that could be a little bit weird. So is there any work that tries to relate this matrix model interpretation and the JT gravity in a different way? Because if you just stick to the strict JT gravity case, you cannot follow this method because of this infinite center charges.
I think you can. I don't see why not.
What I mean is, you can understand first this for generic B primary.
Yeah.
And then consider limit, B goes to infinite limit as a case explaining this duality between JT gravity and matrix model. I agree with that.
Yeah.
But is there any other try to understand this relation between matrix model and JT gravity, just focusing on that strict limit case, without involving this picture for generic B? I'm just wondering.
Now that I know it, through a string theory. Of course, like the original JT matrix integral was done with a path integral, right? By the work of Sash and Stanford. There's another one from string theory, but it's also this limit, type of limit. So it's like if you take the 2, p minimal model and take p to infinity, you also get JT gravity. This one is a continuous version of that if you want.
Any more questions?
Thank you.